Vediamo. Okay, so I think we should be streaming now. So we are back now with Matteo Salvadasio to see the correction of his exercise on modeling concentration-driven processes with Plumed. So Matteo, go ahead.
Thanks, Giovanni. So in this session, actually, we're going to go through the masterclass on modeling concentration-driven processes. And in particular, we're going to look at the 4 exercises and a possible solution for all of them using actions and features that are present in Plume. So just as a recap for the masterclass, the aims of this masterclass were essentially focused on being able to analyze and perform simulations, atomistic simulations, using Plume as an engine to interpret the trajectories or to direct the dynamics by introducing a bias for concentration-driven processes. So processes where the phenomenon that we're interested in analyzing and characterizing the simulations is actually driven by a difference in concentration between different regions of the simulation box. So as objectives of this exercise, we had being able to write Plume files essentially to analyze trajectories and perform simulations using SIMUMD, which is this technique that introduces a bias in order to maintain a constant composition in certain regions of a simulation box. And in particular, the analysis will be focused on using 2 features of Plume. One is multi-colvars, and the second one is Dfs clustering implemented in Plume. And instead, the performing simulations with SIMUMD will actually, I mean, the two examples will feature a couple of different flavors of SIMUMD, symmetric and asymmetric concentration control, and the analysis will actually take advantage again of the same type of tools. So essentially, the 4 exercises will build a kind of a progressive path to being able to characterize what happens in these simulation boxes. So I will use a solution. So I will switch back and forth between this page and the solution, which is available through GitHub in the form of a Jupyter notebook. But of course, solving it in any other format would be perfectly fine. So the first exercise is focused on analyzing a nucleation trajectory. So analyzing a trajectory in which we have a system that starts from an out of equilibrium state, and by overcoming a free energy barrier, which in this case is very small, undergoes a phase transition. And the process in this system actually unfolds by the formation of a population of clusters that then coalesce and form a single droplet. So the trajectory of this first exercise, of this first example, looks a little bit like this. This is the initial state, which is a supersaturated vapor. The model is just a Lennard-Jones type of particle. And as the simulation progresses, essentially, since the chemical potential of this vapor is higher than the chemical potential of a liquid at the same temperature and at the same temperature, basically we observe the formation of a liquid phase. This nucleation process is very fast, and it leads to the formation of this spherical droplet, which here is essentially shared between periodic boundary conditions of the simulation box. So this is how the trajectory looks like. We start from this very dense vapor phase, and we form a liquid droplet in equilibrium with an environment that has a constant density. So the first exercise was focused on essentially being able to count the number of atoms that undergo a transition between the vapor and the liquid phase. And in order to do that, we implement a criterion that is inspired by the work of Ten Voelde and Frankel. So basically, we are just saying that every atom that has a number of neighbors that is larger than a certain threshold is in the liquid phase. And that threshold is set to 5 for this particular system. So we're saying that every atom that has more than five neighbors in its coordination shell is in the liquid phase. And in order to compute this quantity with Plumed, we can use a multi-Colvar, which is a coordination number. So essentially here we define an action that uses coordination number, where the species are all the particles in the system. We define a switching function that defines the cutoff radius within which we're going to count the number of neighbors. And then we apply this action, this multi-Colvar action on coordination number, which is more than. So basically, we are getting essentially we are counting the particles that have a coordination number larger than the threshold set to 5. And then we're just printing this quantity into a log file. So the solution for this looks somewhat like this. So basically it reflects quantitatively what we observe in the trajectory qualitatively. So the system starts where essentially no molecule is in the liquid state. So there is there are no atoms that have a coordination environment denser than this threshold number or threshold value that we identified. And then this number rapidly grows until it reaches a steady state. Okay, but the dynamics of this type of system is not limited to this conversion between a vapor to a liquid that we observe both in this plot and in the trajectory. Actually, one can characterize, for example, how the surface changes as a surface of the liquid droplets that form in this process change as a function of time. It's an interesting property to track, and in fact, as an independent type of exercise associated to this first example, I was suggesting to use multi-Colvar keywords to actually count not just the number of atoms that belong to the dense liquid phase, but also the number of atoms that are on the surface of these droplets that form in the system, and then compute how the surface to volume ratio changes as a function of time, which is I mean, it's an intuitive property of this type of systems. You know, as the phase transition takes place, traditionally these processes are interpreted within the context of classical nucleation theory. So if I go to this trajectory and I switch back to the beginning, so at the beginning, essentially, so we have a driving force for the process that is constituted typically by two parts. One is a negative contribution that comes from the negative difference in chemical potential between the dense and dilute phases. So in this case, the liquid and the vapor phase. And then there is a positive contribution to the free energy, which is associated to the free surfaces of the liquid that are formed. So at the beginning, we rapidly form many clusters because the nucleation rate in these conditions is very large. But as the system progresses towards a steady state, clusters tend to coalesce in order to minimize the surface to volume ratio, because minimizing the surface to volume ratio corresponds to minimizing the free energy for the system given a certain number of given a certain liquid volume. So the question is whether we can characterize quantitatively this process using Plume to analyze the trajectory directly, computing functions of the coordinates of these atoms. And in order to do that, again, we can go back and use multi-Colvars again. So in the solution, there is a little sketch how this can be done. So one can actually use another multi-Colvar action, in this case between, paired with coordination number. Oops, I want to do that. And And basically now I will be defining basically a new action. I'm labeling it surface, which is defined by using coordination number on the same set of atoms with the same switching function for the coordination environment. And then instead of more than, I'm just using between, and I'm defining a cutoff between 5, and I'm defining a region between 5 and 8, where 5 and 8 are the number of neighbors of Lennard-Jones atoms. And I'm doing so because the Ten Voldem-Franke criterion basically allows to incorporate to define liquid-like particles not based on their maximum coordination number, but based on the minimum coordination number that an atom should have to be considered liquid. So atoms on the surface that way are considered liquid. So in this case, I'm defining as lower boundary for the between action 5, which is the same threshold I was using earlier, and as upper boundary 8, which is a kind of a lower bound for the coordination number of these atoms in the bulk of the liquid phase. And then one can compute the ratio using MathEval and computing the ratio between the bulk atoms and surface atoms. Surface atoms and bulk atoms as a function of time. So the final Plume file looks a little bit like this. So you have your bulk, instead of having just a liquid statement, you have a bulk action and a surface action and a ratio, and then a printout of the log. And basically, this is how the bulk and surface atoms look like as a function of time. So you see that at the beginning, the number of surface atom or surface-like atom, and basically atoms that have a coordination number between 5 and 8 is larger than the number of atoms that have a coordination number larger than 8. And then at some point there is a crossover, which qualitatively means that at some point in this period of time, the droplets are big enough so that they actually have a bulk. So that some of the atoms can be considered in the bulk of the liquid phase. And then as the system evolves, the surface atom decrease while the bulk atoms increase. And until we get to a steady state. And the final steady state, as you can see from the trajectory, it's a single droplet that will have a fixed ratio between surface and bulk type of atoms. And this type of behavior is reflected by the surface to bulk ratio, which essentially at the beginning is much larger than 1. So basically, at the beginning, the system is entirely surface, and then as the process goes on, it decays and gets to a steady state that represents that final single spherical droplet. It's also
sorry, Matteo, can I ask
yes.
a question on this point? So
yes.
So this is just for analysis, right? But let's say that you want to add a bias potential, like with metadynamics or umbrella sampling. So which of these variables would be best to to describe the growth of the clusters? Or
so this is an open. I mean, this is for a liquid. It's a question that has an answer, but in general for nucleation problems, identifying an effective reaction coordinate is a kind of an open research question. So I would use as essentially as a reaction coordinate, as proxy for a reaction coordinate in this type of systems, I would use the number of atoms in the liquid phase, so the equivalent of the bulk in these plots. And the reason for that is that typically, I mean, there have been studies, for example, from Baron Peters, that highlighted that the best reaction coordinate for this type of processes is the size of the largest cluster in the simulation box. However, there is a trade-off between the cost of the variables that one can use to bias a system efficiently and how easy and their quality. So I think that a reasonable compromise is an approximation of the size of the largest cluster, which is better approach if you use the number of atoms in the bulk than the number of atoms on the surface, for example. Also, the other thing that's worth saying is that the dynamics in this system are extremely fast by choice. I mean, this is an exercise that needs to be done very, very rapidly. So you can see the entire development of the process from the very initial stages to the stage in which you do have a single cluster and a steady state with a perfect spherical shape, which would be the thermodynamic shape for this type of system. Typically, if you have interesting systems, simulations are far from being so exhaustive in sampling the entire process. So that, yeah. Do I answer your question, Giovanni?
Yeah, thanks.
Okay. Okay, the other thing I plotted that I think was interesting was the ratio as a function of the total number of Lennard-Jones atoms in the liquid phase, just to show that essentially the system is trying to minimize the surface as the size increases. Okay, the second exercise is still based on this trajectory, still based on the same example, but essentially goes a little bit beyond looking at just the number of atoms in a specific specific phase, but actually looking at the configuration of the system and how the transition happens in terms of the formation of a population of clusters that then coalesce to form the final steady state droplet. So in this case, the exercise is essentially taking advantage of the Dfs clustering action in Plume, which I think comes with the adjacency matrix module. So if you want to use this action, you need to remember to compile the code with that module active. And in this case, basically what we are doing is, okay, we are defining, again, using multi-colvars, an action that identifies atoms with a large coordination number. And then we are passing this set of atoms to this action contact matrix that defines a contact matrix. From the contact matrix, we are feeding this contact matrix to the Dfs clustering action. So essentially, here we're saying that every atom that has a single neighbor, sorry, that is adjacent to a single atom that has a high coordination, so that is within this pool of atoms Q, is used to build this contact matrix, and then DFS identifies clusters in the contact matrix. Now, DFS is based on this idea that an adjacency matrix essentially represents a graph in the system. So by identifying the connected components of the graph, one can identify what are the clusters in the system. In other words, if we find every set of nodes that are connected in this undirected graph identified by the contact matrix, we are identifying the size of the largest cluster. In this case, we are defining as nodes every one of the liquid-like Lennard-Jones atoms that are in the system, and the connection is defined when two of these nodes are within this cutoff radius, which is the same cutoff radius that we are using in the coordination number statement. Now, the DFS clustering action gives us a number of options, and if you want, you can go and look at the documentation for this action. But for the purposes of this analysis, I'm using two of them. One is essentially a counting option, which is given by this cluster n atoms action that allows us essentially to count the number of nodes in the graph that belong to the largest, second largest, third largest, and fourth largest connected component. So in other words, with these actions that here are labeled the cluster 1, 2, 3, and 4, we are getting the size of the connected component within this contact matrix, which correspond to the size of the largest cluster, second largest, and so on. And then the second action that I'm using based on the DFS clustering action is the so-called cluster distribution. So in both cases, we are feeding we are feeding to this action the clusters identified with DFS. But in this case, I'm counting the number of clusters that is larger than a certain threshold. So in this case, in the first four statements, basically, I'm computing the size of the 4 largest clusters. In this statement, instead, I'm computing the number of clusters that have a size larger than a certain threshold. And in this case, the threshold is very small. Basically, it's 2. Essentially, I'm counting every possible cluster from dimers up. And the information that's provided by these two actions is slightly different. So this one gives you the size of a single cluster. This one instead gives you the number of clusters. And then again, I'm plotting everything. I'm printing everything to a log file, and this is the usual statement to print everything to file. So this first part looks a little bit like this. So the number of clusters. Remember that the threshold now for the definition of the number of clusters is very, very low. So basically, I'm considering a dimer already a cluster in this type of definition. And so the system at the beginning was very dense, and probably there's a high population of dimers in that initial configuration, and the number of clusters decreases as a function of time. Here I use the log scale just to show the trend a little bit better, but basically you start from a large number, and then you go to essentially something in the order of 10 clusters that have size 2 or larger at steady state. And the growth of the 1 to 4 largest clusters instead is represented in this second plot, where basically I'm plotting the time series that come out of these four n-atom actions. And so you can see that basically at the beginning you have a regime in which the scale is not perfect, but basically in the very first stages the four largest clusters are growing all at the same rate. And probably if you want to plot clusters that are smaller in this ranking, actually you would see that at the very beginning the rate of all these clusters is exactly the same, but at some point you start seeing these discontinuities in the size of the cluster, and these discontinuities actually represent instances in which 2 clusters coalesce and form a bigger one. So essentially the blue cluster at the beginning is competing. So at the beginning, there is no clear-cut winner in this ranking. But then here you have a first event in which a coalescence event takes place, and then another one, and so on. And as the time passes and the number of clusters diminishes, as you see here, basically you can actually interpret a specific event that happened in the system. So at this point, there is a set of configurations between frame 100 and 200 where there are 2 competing clusters, and this is the event where these 2 competing clusters actually come together and form the final spherical droplet. And actually, knowing this, one could also go back and look at what happens to the features of the total number of liquid-like, bulk-like, and surface-like particles. And I think it's interesting because you can see that in the very same instant where the coalescence happens, actually the number of surface atoms decreases and the number of bulk atoms increases, which is interesting because basically the total number of particles in the liquid phase is more or less the same at this point, before and after the jump, but and I think you can see it from here. There's a tiny jump, but it's not that significant. But here you see these discontinuities because the system is reorganizing itself to diminish the surface and at the same volume basically. And just to check that I'm not saying random stuff. Let me see if that around frame 200 here. Okay. So this is in that part of the trajectory, you have two droplets, and then around frame 200 they coalesce and form a single droplet. So this type of process can be characterized quantitatively using this type of functionalities implemented in Plumed. There is an additional thing I wanted to plot, which is sometimes it can be misleading to plot the number of atoms, in the sense that this scale as the volume of the clusters, but sometimes we interpret size better as the radius or something that scales with the linear size of the clusters. So if we take the cubic root of that number of particles, you get functions that or trends that look easier to interpret in intuitive terms, in the sense that in this case, the quantity that we're plotting on the y-axis scales as the radius of the clusters, and it's a little bit more intuitive. In fact, I think my qualitative interpretation of what's happening is closer to this than to a counting process. Okay. Then, as an additional step for this exercise too, I was suggesting to try and essentially edit this Plume file to change the criterion for the number of clusters, for the threshold on the counting of the number of clusters. And I was suggesting to increase it to a much larger value, in particular to 20. So this is basically, one can readily do that by changing the criterion for the number of cluster counting. Basically here I'm changing the position of the switching function on the more than action that acts on this cluster distribution action. And this is how the trend looks like, which I think it's interesting, because now the clusters that are counted in the system are not including the small species that act as that would be present and are present also in a vapor in equilibrium with the liquid, but actually counts liquid droplets or objects that resemble more closely liquid droplets. And in this case, you see that there is an immediate increase in the number of these clusters. Again, the resolution here isn't great because I have reduced the size of the trajectory, but in principle, one could gather a few points in this regime to better appreciate the nucleation rate at the initial concentration conditions, and then the number of clusters decreases, and reaching a condition in which essentially there is only one cluster at steady state. Okay. I also plotted the surface to volume ratio as a function of the number of clusters, and you see that basically it has these. I mean, again, the number of points here isn't great. So let me see if I can make it a bit clearer if putting in some. If I put in a line. No, never do this type of things. I have to. No, I know what's happening. Wait. Okay. Basically, I just wanted to highlight this type of behavior where you start from essentially forming a large number of clusters, and the surface to volume ratio is large, and then you go through this type of process where the number of clusters increases a lot. So the surface to volume ratio and the number of clusters increases, but their size also increases. So the surface to volume ratio decreases. And then the clusters start to coalesce, and this is the dominant trend, and you get to the steady state where you have just a single cluster and with a surface to volume ratio that is the minimum one that the system can achieve. Okay, Giovanni, is there anything I was particularly?
No, just maybe one curiosity, because it's related to my question on exercise number 1. So now if you, let's say that you use the size of cluster number 1 as a biased collective variable. So first, how expensive it would be, and second, so you have these jumps. So in theory, these variables are made continuous with switching functions, right? So that means that when two clusters are getting, so you have no force when the two clusters are far from each other, and then at some point you feel a sudden force, maybe.
Yeah, I agree with you. In fact, if you scout the literature, we've never really used it as a reaction coordinate, except in the paper where these ideas were published. There is this paper from 2017. There is a small Lennard-Jones simulation where the largest cluster has been used as the reaction coordinate, as the bias variable. But it's a very special case because first of all, it's a system that's small enough that you never have this re-ranking problem that leads to discontinuities in the forces. So it's a system in which you only form one nucleus, and that essentially and that nucleus grows. And then the other thing is that if you look at the number of particles in that example, you quickly realize the computational cost of these things. I mean, it's at the moment is not really practical to bias any meaningful simulation using this as a reaction coordinate. But I think it's a very interesting feature to have, because one can bias a variable that is strongly correlated to this one, for example, the total number of atoms in the liquid phase, and then reweight as a function of the largest cluster size, which will give essentially give you good sampling of the configuration space you need to converge a free energy surface. And then you will get the free energy reweighted on a reaction coordinate, which is the typical one used for theoretical studies of this type of problems. Yeah, it's in principle it's continuous. It has these problems that you highlighted, but I think it's a very good feature to have in order to on the fly analyze this type of trajectory directly having a quantitative estimate of the largest cluster size. Makes sense?
Yeah, totally.
Okay. Okay. Now the third and fourth example are actually based on. I mean, all this discussion on the nucleation trajectory is taking place in a system in which the driving force changes as a function of time. In fact, as the droplet increases in size, the concentration or the vapor pressure actually in the simulation box decreases, and you can appreciate that qualitatively just by looking at the trajectory. So basically, when somewhere here, the density in the vapor phase is higher than at the steady state, even though perhaps that was not very easy to see. The thing is that basically the density of the vapor phase is changing as a function of time. This means that the driving force for the formation of this droplet changes as a function of time. And in some conditions or some situations, this is perfectly fine to accept in these simulations and can be taken care of. But there are other conditions in which one may be interested in essentially defining a constant driving force type of problem. So in this particular case, in this masterclass, there are two exercises that try to target this idea. And the first is actually based on analyzing a diffusion process. So analyzing a diffusion process by imposing a stationary difference in concentration between two regions of a simulation box. And this is achieved using SimuMD. And basically, here there is the system that is this one. So this let me see. This one here is the system that we're looking at, and the problem that this exercise targets is basically is focused on essentially investigating the diffusion of these Lennard-Jones particles across this domain under the effect of a constant difference in concentration across the domain. So essentially, what we want to run in this case is an out of equilibrium simulation where particles diffuse freely from a high concentration region to a low concentration region. And this is achieved by essentially, let me go. This is achieved by, again, defining a group of atoms, in this case, all the atoms in the system. This is a smaller example because this exercise requires you to run a small GROMAC simulation with Plumed. And so there are only 1,000 Lennard-Jones particles. And then we define, with the SimuMD action, we define two regions that we want to control. One is on the left of the simulation box, and the other one is on the right of the simulation box. The particles that are fed into both these actions are the particles identified by the Lennard-Jones group, and basically here we are imposing. Well, actually, it's easier if I show it on the trajectory. So here, as the simulation progresses, basically what happens is that the system reaches a steady state in which the concentration on this side of the simulation box and on this side of the simulation box are held at a constant value. And within these two regions, there are no biasing forces. So basically, the concentration gradient that develops between the high concentration and the low concentration region is actually dictated only by this difference in concentration. And the biasing forces that maintain constant the composition in these sub-volumes of the simulation box that we're calling control regions are only applied between the control regions themselves and the reservoir, which in this case is ended up on this side. But again, there are periodic boundary conditions in this type of system. So this means that this trajectory essentially, or the sampling of this type of stationary conditions can continue indefinitely as a function of simulation time. The trajectory is not infinite, so now it's looping. But that's what's happening there. And so in this case, so this is defining the left and the right. These are defining the left and the right controlled regions. The size of these control regions is defined as a distance from a stationary point. So fixed at 0.5 means that the reference point for the definition of these two volumes is defined in the middle of the simulation box on the z-axis of the simulation box. And so this type of statement is using fractional coordinates. So whatever your z is, this is in the middle of it. And then the distance from the reference of the control region is 25% of the length of the z simulation box. And then the controlled region itself is 10% of that length. And then this is a parameter that controls how steep the switching function that applies forces at the interface between the interface between the reservoir and the physical system is. And this asymmetry keyword is essentially telling to this statement that we want to control independently the composition of two regions, and this one is on the left side of this reference point. And these instead are parameters that are associated with the calculation of a density profile that can be used in this type of statements to define adaptively where the interface of a dense region is. There is I mean, more information on the keywords associated with the SIMUMD action is available on the GitHub on a GitHub account, and I think it's linked here as well, somewhere.
Or you can copy it here from the
yeah. But I think just as a nope, that's the paper. Sorry. Yeah. Anyways, I'll make it a little bit clearer where more information can be found. But in this, so this is the first part of the action, and then so this is defining this number density in these controlled regions independently on the left and on the right, and then the forces are applied by computing, essentially by using the restraint action that applies an harmonic force to this action, essentially to the density of this controlled region. And okay, so essentially this Plume file does these things, and then basically prints out a log file that essentially is reporting the density in the left and right controlled regions and the bias acting on the left and right controlled regions. So just to follow what's happening in that trajectory that I just ran, you can see that after an equilibration, what happens is that the left control region is constant at a certain number of Lagrange particles per unit volume, and the right control region remains at a constant composition at low concentration. And just to understand better what's happening, here I'm just plotting the value of the restraint as a function of the value of these number densities on the left and right controlled regions. And you can see that essentially, yeah, what you already know, that the restraint is an harmonic restraint on that set point, and the set point in the right on the left control region is higher than on the right control region. And as an independent part for this second exercise, a third exercise actually, I was suggesting to perform simulations at different differences in concentration, and then compute the concentration gradient across the simulation box and compare it essentially between different cases. So this can be done again in Plume using multi-Colvars. So in order to plot the density profile, compute and plot the density profile, one can use the multi-Colvars density and the action multi-Colvar density that allows to compute a grid of multi-Colvars in the simulation box. So in this case, I'm defining a reference point by essentially introducing a fixed atom in a position that corresponds to the mid. Essentially, I want to have a reference point, a reference frame that is the same as the reference frame used by SIMUMD. So this is midway through the z-axis of my small simulation box. And then this density action is a multi-Colvar action that computes the density of these species, all the particles in the system. And then I'm plotting the multi-Colvar density using as an origin the reference point given by this virtual atom, and as data the output of the density action in the z-axis, on the z-axis with 100 beams, a certain bandwidth, and a certain stride. The usual histogram type of keywords for this type of actions, and then I'm dumping this into a density profile. And in order to run simulations at different concentrations, one can simply reset the left set point from the previous Plume file, run again, and essentially see what happens. So this is a plot. Here I'm recapping what happens in three cases at three different densities. 0.5, 1, and 1.5 Lagrange atoms per nanometer cube. in the dense controlled region. So on the left control region for this system. So basically here the continuous lines represent the output of the multi-colvar, the output of the multi-colvar dense on this grid, and yeah, and then you see that the concentration is decaying following this exponential trend, which is what you would expect in a purely diffusive process between the source of this between the source, which is the left control region, and the sink, which is the right control region. And something that I wanted to highlight is that, for example, in this case, for issues of computational cost, and essentially to make the exercise viable to be performed on a small machine like a laptop or similar, basically the number of atoms is very small and the system is in the gas phase, which means that the atoms move very rapidly. So the SIMU-MD algorithm is able to maintain the concentration close to the set point, but this constraint is essentially obtained. It's essentially satisfied on average. And then, since the diffusive process is extremely fast, here you don't have a flat profile. In a denser system, instead, you would see, especially if the diffusion process is much slower than the rate at which particles the rate at which these control regions can be replenished, you would see that the concentration profile is much closer to the average across the entire control region. That said, here the forces that act on the system, the forces associated to the restraint bias that act on the system, are only acting at the interface between this controlled region and the reservoir, which is on this side of the box. And the same happens here, where the concentration is kept low, but then the forces are applied at this interface here. Okay, the final exercise is based on essentially taking all these things, the analysis of the dense formation of a dense liquid from a vapor, and SIMU-MD to investigate what happens in a condensation process at steady state. So in this case, once again, the starting point for this exercise was to essentially perform a simulation in which, using the input files that are provided with the exercise, by keeping essentially the composition constant in a symmetric manner in the simulation box, and maintaining both controlled regions at the same concentration, and leading a process of condensation on top of a static slab type of geometry. So this is the configuration for this type of system. And what happens here is that, we have a similar process than the one we have analyzed earlier, but there are some important differences. So the first one, the similarity, of course, is that we are considering a high concentration in this region and in this region of the simulation box. However, we are not introducing an artificial sink for the diffusion process. The sink in this context is represented by the surface itself. This means that these atoms have a lower chemical potential when they are adsorbed on the surface of this slab than when they are in a solution, or in this case in the gas phase, at constant density as maintained in the simulation. And as the absorption/condensation process in this simple system progresses, what happens is that atoms are transferred from the reservoir to the surface of the crystal, to the surface of the particle. So this is what happens in the simulation. Wait a second, because the trajectory is actually longer than this, much longer than this. So let me speed it up. Because this highlights an important difference, which is in the previous example, once the system reaches a steady state, that steady state can be kept essentially indefinitely because particles are recirculated through periodic boundary conditions. But in this case, instead, we reach a steady state, but that steady state has a lifetime, and the lifetime is dictated by how large or small the reservoir is. So the point of doing this type of simulations is that one could be interested in investigating the dynamics of adsorption under stationary out of equilibrium conditions, so conditions in which the difference in the chemical potential of the phase that is on the fluid phase that is kept at constant density in these regions, and the chemical potential of this state, which is determined just by the physical chemistry of the adsorption process, is constant. And then at a certain point, though, the material balance will catch up with the whole process, and when the reservoir is completely emptied, the process will follow its own possibly its own dynamics, which is not relevant anymore for the analysis of the system. So in the analysis now, basically, one can actually combine many of the ideas.
Sorry, Matteo, just
yes.
one curiosity. So
yes.
in the code,
yes.
when the reservoir is empty, is there some like warning, or just forces are continues to grow, but there's nothing more to bring in,
no, well,
right?
Forces are not growing because it's a static bias. But there is nothing. There is nothing that falls within the range of the.
I thought that because the concentration is too low, the forces that try to bring particles from the reservoir grows and.
Yeah, but there is no essentially the position of the atoms, essentially it's not the forces grow. There is no special trick that happens when the
but the atoms are not affected because there's no atom there.
Exactly, there's no atom there, exactly. And I just want to show that you see this qualitatively. Then I want to show how essentially this effect shows up in different aspects of the things you can monitor when one of these simulations are running. And so the first thing that one can actually monitor is the set point of the concentration in the two controlled regions. And you see that basically for around 8,000 frames, the simulation is evolving under this constant composition in these regions. But then at a certain point here, you reach this limit where the essentially adsorption on the slab has taken place, and the number of atoms that has been removed from the reservoir is so large that the reservoir that the algorithm cannot keep up anymore with the replenishment of the control regions, and this concentration starts to miss the set point. So in these conditions, yes, the forces would be large, but they will be localized in at that interface, and the net effect is that you will not be able to keep the set point where you want it, basically. And again, in analogy to what was done earlier, this is how the two restraint potentials look like for this type of system. And in this case, the blue and red and blue and yellow curve are actually overlapped because we're setting exactly the same target concentration for this type of process on both sides of the membrane. And then the analysis that I've done after that is based on combining many of the ideas that have been shown in the previous three exercises. So first of all, I think it would be interesting to monitor, for example, let me get there. Okay, the number of atoms in the liquid phase, because that would tell us essentially essentially how the adsorption dynamics happens under the effect of this constant composition regime. And then yeah, and then I'll show you that the fact that basically one can also try and use other features that are available in Plume to make this work as quantitatively as possible. So basically, my objective here is to monitor. First of all, is to monitor the total number of liquid-like particles in the system, and then I'm also interested in monitoring the number of particles that are actually adsorbed on the surface versus the number of particles that are in the reservoir. So one can essentially use the same liquid-like Ten Volden-Frenkel liquid-like criterion that we used in the very first exercise to count the total number of liquid-like Lennard-Jones atoms in the system. And then by taking advantage of these around statement that can be used with the data coming out of the coordination number action, one can actually compute how many of these particles are within a certain region of the simulation box. So in this case, within a lower and an upper limit around the slab. And then one can do a similar thing to count the number of particles in the reservoir, so on the left and on the right. And then here I'm just using two different statements for the two symmetric sides of the simulation box, and then I'm summing them using Mateval to have a total number of particles in the reservoir. And this is fine, but I'll show you. Basically, this is giving us kind of a compound representation of what happens. So this is the total number of, the blue is the total number of liquid-like particles or liquid-like Lennard-Jones atoms in the system. And it starts high because these atoms are already liquid in the reservoir. So even when no adsorption has happened, you have basically almost all the particles in the system have a liquid-like character based on that criterion. And then as the system reaches a steady state, you have a decrease of this number because particles are transferred from the reservoir to the surface, and then this number slightly grows following this blue trend. Now, conversely, one can follow the number of liquid-like Lennard-Jones atoms in the reservoir, which is this orange one, which starts high and then goes down and goes to zero, exactly where we think it would when our system is not able to cope anymore with the process. And then the green curve instead, or the green data set shows the total number of liquid-like Lennard-Jones atoms that are adsorbed on the slab. So this is actually the output of this adsorption or adds labeled around action. So basically, we are counting the number of liquid particles, not everywhere in the simulation box, but just around the slab. And then you see that this actually behaves as one would expect. So it starts from zero when nothing is adsorbed, and then there is a period in which the number slowly grows until it reaches this regime where the adsorption is at steady state and the number of Lennard-Jones particles increases almost linearly. Now, an interesting thing is that here we are not counting the particles. So in this case, we're just computing like the total number of particles in this region. But we are not differentiating, for example, what happens on this side or this side of the slab. But in order to do that, one can actually and to follow the growth of these layers, adsorbed layers. On both sides of the slab, one can actually take advantage of the clustering again. So this is what I did. I did here. I would basically I defined again a contact matrix where I'm just passing the total number of atoms that are adsorbed. So I'm passing the output of this around action based on the coordination number action. So I'm passing all the adsorbed liquid-like atoms to the clustering process, and then I'm plotting the two largest clusters, the size of the two largest clusters, which are the two, arguably are the two sets of particles on both sides of the slab. And yeah, I'm trying to look at. Yes, and that's what you see with these red and purple trends. And the interesting thing is that basically the slope here is very much consistent with the green one, in the sense that here you have the green slope is like twice these individual side slopes. Actually, we can actually try to. Not sure. Try to check whether this is true or am I saying something incorrect. Yeah, more or less it's. I mean, the criteria are slightly different, but if we average what happens on the total number of adsorbed particles on both sides, I mean, to account on average what happens on both sides, we get a slope that is compatible with what we get from the clustering of the two adsorbed layers. And then again, one can use the same ideas we used for the density profile in the diffusion case to investigate what happens in the system. And this is how the system looks like. So basically, so let me recap what you're seeing. So you have essentially two density profiles that have been computed in two different averaging two different sets of coordinates from the time series coming from the simulation. One is between frame 500 and 1000, and the other one from 1000 and 1500. So basically, this region and this region of this evolution in time of our system, and the blue density profile is the density profile of the slab, while basically the red and blue intervals here represent the two controlled regions, where again the concentration is kept constant on average due to the fast diffusion of the model. And to be honest, in order to avoid condensation and another problem is the temperature of the simulation is higher than the temperature of the previous simulation, and in fact diffusion is faster, and this averaging is even more important. The other thing I wanted to highlight is the fact that what happens is that our system is accumulating stuff at the interface, but this process is taking place under the effect of an average constant difference in chemical potential between this region that represents the bulk of the system and this region which represents the interesting portion of the system where absorption is completely driven by the interactions between the slab and the particles. The black lines actually represent the region in which I've done this I've defined this around keyword. So those limits actually represent that portion of the simulation box where the multi-Colvar adds and res, or labeled as adds and adds and res have been computed. And so I think that's all. Just perhaps I mean a recap on the spirit of this whole thing. Basically, the idea here was, okay, Plume typically is used for biasing molecular dynamic simulations, computing free energies and computing collective variables. in this case, I think the aim of this masterclass was to highlight that it can be used also to interpret and extract quantitative data from trajectory for this type of processes. And again, the first two exercises are on just analyzing trajectories. The second two exercises are based on using SimuMD. And in particular, the final one, in its spirit, wants to essentially include all the things that have been showcased in the previous examples, essentially.
Okay, great. So thanks a lot, Matteo. I will stop the streaming now.